Hello and welcome to BYJU'S JEE. My name is Ashish and we have a special video for you from chemistry. The JEE Main Exam is over, the JEE Advanced Exam is right around the corner, and we're going to give you some tips and tricks to solve a few very interesting questions that have come in the last year JEE papers. Now, I'm going to be honest with you. Not a lot of questions out of the 36 questions that we've had so far usually are solvable by just using a trick in a couple of minutes. Yeah, but even if you're able to solve 5 or 6 questions by using some sort of trick and save some time, you can use that time in the other questions that may be a little bit difficult. The JEE Advanced has some tricky numericals and questions. So, play to your strengths as usual. All the best with your preparation. Let's get started right away. Here's a very interesting question. Yeah, there are 3 columns given to us, and there are 3 questions that follow on these columns. Now, if you see this is from atomic structure, it's really intimidating. The first column is kind of, it's okay. It talks about the 1s orbital, the 2s orbital, 2pz, and 3d z square orbital. Okay. Second column has psi and a lot of scary stuff. Yeah, if you ask me, this is the solution to the Schrodinger wave equation. That's what psi is usually. When you write psi, that's what that means. Then the next one says 1 radial node. Another solution to Schrodinger wave equation. This has theta. The first one did not. The last one is something about a nodal plane. Column 3, there's a graph. Again, psi versus r by a naught. Probability density at the nucleus was given to be proportional to something. And another option about probability density. And the last one, that's an entire numerical on its own, right? Energy needed to excite an electron from state n equal to 2, n equal to 4. This is the emission absorption idea. Okay, so looks scary. Let's look at the question. Let's look at the first question. I just quickly went through what the graph is about. Well, the first question talks about the He plus ion, yeah, for this, which is the only incorrect option. That's what we need to figure out. Now we're going to be smart here. Okay, what's the approach going to be? Let's look at the options. All of them talk about the He plus ion. Now this is a hydrogen-like species. Okay, and look at that. There's only 1 and 2 from the first column that are being spoken of, which means 1s and 2s orbitals. And so this is going to be our key starting point. We're going to look at the properties of 1s and 2s orbitals. What are they like? What are they not like? With respect to the other columns. And then we're just going to eliminate options. Let's get started right away. So what are the 1s and 2s orbitals like? They're both spherical. Yeah, that's the first thing you need to know. Simple idea, but the most important starting point. Okay. And what we're going to do, we're only going to look at the first and second column and arrive at the answer. We won't even look at the third column. I'll tell you why. It's a trick. So they're spherical, and you know for sure that psi square, the probability density. See, psi is the solution to the Schrodinger wave equation. Psi square is a probability density. You'll know this if you've just read atomic structure even once. Yeah, just go through it. This, if it's spherical, will not depend on theta or phi. What are theta and phi? If you look at spherical coordinate system, yeah, you have r, which is the radial distance over here, and there's some angle theta and another angle phi. Yeah, this in 3D there would be another angle over here phi, which would be basically moving it this way. Yeah, if you move it there, then that angle is phi. So what I'm trying to say here is that since it's it's going to be symmetrical around all axes. But if it's spherical, psi square is not going to be dependent on theta or phi. That's a very important idea. Again, a little bit of just simple theory, you'll be able to know this and recognize this. And lastly, there's some mention of radial nodes, right? So radial nodes is simply very, very basic idea. Even if your target is JEE Main, you would definitely know how to do this. And radial node is n minus L minus 1. For 1s, it would simply be 0, right? N value is 1, L is 0, and minus 1, there you go. And 2s, you have 1 radial node. What does that mean? I'm quickly writing this down because this will make your life really easy. Yeah, 1 radial node. That means that this graph over here, which is in the third column, matches that. You see this point over here? Since this graph crosses this axis, the r-axis once, that means there's 1 radial node. All basic theory that you would definitely know. But the question itself is so intimidating because of psi and all that, you may be a bit scared. You know where I'm going with this? We already have the answer just by these ideas, yeah? Trust me, you already do. There are 2 options which match 1 with 1. Okay, now what was 1 with 1? Let me look at that quickly. So 1 with 1 was 1s orbital and that scary looking psi function. I think it could work. I'm not sure, but it could work because there is no theta or phi there, which means that, yeah, this looks like this could be a solution to a spherical a node there. Yeah, so 1s would be a spherical orbital. So yeah, I think that could work. but we need to figure out the incorrect combination. So looks like one and option A or option D could be correct. Option B is 2 and 2, which is 2s, 1 radial node. This works too. This also could be correct. Now, if I was lucky and I looked at option C directly, I know for sure it's going to be incorrect because it says 1 and 3. What are 1 and 3? 1 is 1s orbital and 3 was psi depending on theta. We already said that that's not possible. Yeah? Why? Because it's a spherical node. It's going to be symmetrical across theta and phi, so it's not going to be dependent on theta or phi. That's the answer. That's the incorrect option. And that's your trick right here. If you spend time on the third column S option, proving that it is correct, no doubt. But that would take you a lot of time to solve it. As I said, it's like a JEE main question by itself, solving that thing. So there you go. The answer by this quick trick is simply option C, which is incorrect. And there you go. Let's look at the other questions, and they are also very, very simple to do, and they're all linked. That's a thing. In questions like these, when you have a passage or this sort of a matrix match kind of, it's not strictly matrix match, but you have like 3 columns and the question after that. If you do the first question, the rest of them become really easy. We'll look at the next question right after this. Second question, a part of the same 3-column thing that looked really scary from atomic structure. Now, in this question, we're talking about only correct combination for any hydrogen-like species. That's what we're supposed to figure out. 4 options given to us. Let's see. What's the approach going to be? It's going to be very similar to the last one. We're going to eliminate options. And the deal is, look, what are hydrogen-like species? They have 1 electron each in them. Yeah, that's something you already know. And what happens to the options? Look at the other options. All 4 of them have 1s, 2s, 2p, and 3z, 3d. Yeah, so if they're all there, then we're going to have to look at all 4 of them. It's a little tedious. It's not. Identify this. We're going to eliminate options. What's the goal going to be? Look, 2 options have the Roman numeral 2 in them, so small Roman numeral, which means we're talking about second column. And 2 of them talk about P. What was P? P, remember, is this graph right here, right? That goes like this. Now, this has 1 radial node. This we already figured out in the first question. Now, it looks like all we need to do is figure out the number of radial nodes for the 4 orbitals, and I think we can get to the answer just by doing so. Let's see. What's radial nodes? Formula is simple, right? N minus L minus 1. So I'm going to quickly write down for all the 4 orbitals what that's like. Yeah, so 1s, 2s, 2p, and 3d. The n values are over here in the first one here. This is n. These are L values, and the minus 1 is constant. So with that, you get the number of or the radial nodes to be 0, 1, 0, and 0 respectively. And just from here, we can eliminate 2 options. Which ones? Look carefully. In option B, we talk about 1 matching with 2, which was that 1 radial node, this idea. Clearly, 1 does not have 1 radial node, has no radial nodes, right? That's out of the way. That's definitely not correct. And we also eliminate option D. D is 3 matching with P, which again is, guess what? 1 radial node, right? But in the graph format. So that's not true. It has no radial nodes. So this one's out too. Halfway there. What you do from here is up to you, whatever you're comfortable with. You can either figure out which one is wrong or get which one's correct. So 2s has 1 radial node that we already established, and that's the correct answer. If you recognize that, that's great, and that should solve the question. Or you could also figure out that, look, in 3D, psi square, or the probability density, is not maximum, it's minimum at the nucleus, which makes this one incorrect. So quickly eliminate options. We got the correct answer to be option C. A quick recap, we needed to figure out by looking at the options that, okay, the first column was 1, 2, 3, and 4, all 4 were there, which means 1s, 2s, 2p, and 3d. And looking at the other options, which was the second and the third, we looked at both of them. So you need to be able to multitask a little bit over here. Once you do that, you figure out that the deal over here is all about radial nodes. We write down number of radial nodes, eliminate 2 options, and the last one also, the one that was correct, also was figured out by the idea of just radial nodes. Moving on to the third question from the same set of the columns, from atomic structure. Now, this is going to seem really weird, okay? In this question, we're supposed to figure out the only correct combination for a hydrogen atom. And our approach is going to be slightly different from what we've been doing before. We figured out that, okay, hydrogen atom or He+, they're all 1 electron species, we'll eliminate options. But in this, we're going to look at the first question. The first question spoke about He+, which is also hydrogen-like. And there, we're supposed to figure out the incorrect option, which means the other three options were correct. And one of those three correct options happens to be one of the options here, which is this 11S guy. Yeah. The other options were 22Q, 21, and 11R. Yeah. So these two are also correct. Looking at the first question, and that is your answer right here. This was a 30-second thing. You take it, move on to the next question. If you want to go into a little bit more detail, we've done that on the app. We've solved these questions, and also on YouTube it's there. You can check it out. But it'll take you a lot more time, and you could also get confused because see, look at one of the options is 21Q. Now, that would be like, how are you supposed to know this is correct? Yeah, 21 means that 2S matches with that side depending on that function. Yeah, looks like, yeah, it could be S orbital, but you don't know for sure whether it's 1S or 2S. The only way to know that for sure that it's 1S is if you looked at the first question, and because that was correct, okay, this one must be incorrect. So it could get fairly confusing if you did it in any other way other than this. So the answer here clearly is 11S, which is correct, and the other ones are not correct. Yeah, 11P is one radial node, which is not okay. Yeah, you know that this has just no radial nodes. Yeah, let me write that down quickly. No radial nodes. 14R, what is this? Yeah, XY. Yeah, sure. There's no nodal plane, right? This is a spherical orbital. Yeah, that's wrong. Answer is 11 and S. Now, this is a very, very interesting question from P block elements. We're talking about oxo acids, specifically HOCl and HClO4. Four options, you could have more than one correct answer here. Look at the options one by one. Our approach is going to be, well, we're going to have to kind of draw the structure. Yeah, we have just two oxo acids here. And we need to use this conjugate acid-base idea. Could be a little bit tricky. Okay, let's get started. So central atom in HClO4 and HOCl, we are being asked what is the hybridization of this. Now you need to realize that central atoms are different in both of these elements, both of these compounds. Yeah, that's really, really important. If you mess that up, you would not get this correct. Look at the way that these compounds form. This is HClO4 and this is HOCl. So central atom in this case is Cl and this one is O. You may be like, yeah, that's a no-brainer. Of course, that's so, but in a hurry, you may mess this up. Both of these are clearly sp3. Now, the mistake you could make is you could write it like this, yeah, that Cl is in the center for some reason, which seems absurd right now, but hey, students have made sillier mistakes. So be careful about this. This is the way the structure looks, and these two, this is basically lone pair of electrons. That's what this is. Let me erase this because it doesn't make sense. They are sp3 hybridized. This option is definitely correct, so mark that right away. Then you talk about what happens when Cl2 and H2O react. This is theoretical. No other way about it. Yeah? You either know it or you don't. This one's incorrect. Yeah, it forms HOCl and HCl. Now the conjugate acid base idea, that's interesting. HClO4 is an acid. Now the option is saying that the conjugate base of this, how does it compare in strength with water? So we make it react with water, HClO4, and we get ClO4 minus and H3O plus. Now this is the conjugate base of this acid. So we are comparing the strength of this, basically the basicity, with that of this, the basicity of water. Okay. Since this reaction is pretty much going to be in this direction because this is acid, very strong acid, HClO4. Water is definitely a stronger base. Let me write that down. H2O basicity is going to be greater than that of ClO4 minus because this is stable. Yeah, this compound is really stable. It does not want to accept H plus. I'm good. ClO4 minus is good. It doesn't want to do that. Why? It's resonance stabilized. And guess what? That's the next option. So the deal is, if you figure this one out, you'll also be able to figure out the next option. Yeah, look at the structure over here. This is what the ClO4 minus ion looks like. And since this is going to be resonance stabilized, oh, I messed up spelling of resonance. Resonance stabilized, yeah. And this one's going to be correct as well. So quickly going over the options. I had four options, right? First one, yeah, they're both sp3 hybridized, but the central atoms are different. One there's Cl, the other one there's O. HClO4 is not formed. You get different products, which we also saw. Conjugate base of HClO4, which is ClO4 minus, is weaker base than H2O. Sure, that's correct too. And because this is correct, you get the next one. Yeah, HClO4 is more acidic than HClO because of the resonance stabilization of its ion, which we figured out, right? This is a lot more stable, and they are linked. Although it may not seem that options C and D are linked, it is definitely linked. How is that? Well, HClO does not have this resonance stabilization. Yeah, if I look at this thing, if I take out this H plus ion away, then I just have OCl minus, which is okay. It's a decent acid, but not as strong as this because of the structure that I showed you of ClO4 minus ion. There you go. Those are the correct answers. Now here's the question where a numerical input is expected as an answer. Now, I don't think I would call it a trick as such, but if you don't figure out how to start it, it's going to seem like a ridiculous question. Like, what are you even supposed to do over here? Well, there are some compounds given over here. We need to figure out which one of them turns red litmus paper blue, which means that they are acidic. No, they're basic. Red to blue is basic. How do you do that? Why would a compound be basic? Yeah, identify that this is a salt, and salts hydrolyze. When hydrolysis happens, then the solution can be acidic or basic. That's the idea here that you need to start with. That's the approach. That's about it actually. To explain a little bit more in a little bit more detail, Ba is a salt, and this is how it would, when you put it in water, it forms B plus and A minus ions. Now, sometimes these ions hydrolyze and they form either this. If the B plus ion reacts with water, it gives you BOH and H plus. So this would be acidic if this happens, or they would go this way. A minus reacts with water and gives you base. Yeah, OH minus, which is a base. So we're interested in this second one over here. Yeah, this would happen if and only if this guy itself is not stable. If it's not stable, then it would like to react with water. If it is stable, like say if this is stable, which means I'd say if this is like Na plus or say K plus, then this is not going to happen. Yeah, it's definitely going to be, this is not going to happen. Yeah, but if it's a weak thing like say Fe3 plus or something like that, then yeah, it could happen. So that's the idea we're going to do. So how is a salt formed? A salt is formed by the reaction of an acid or a base. Yeah, you know this. Let me just quickly write that down. You have acid plus base giving you salt plus water. This is taking time because I'm explaining what we're doing here. Otherwise, the question itself is, you could blaze through it. So now, depending on whether this acid is weak or strong and the base is weak or strong, you get whether this final solution is acidic or basic. Now, if we are looking at this specific condition, yeah, the second one right here, if this is to happen, then you must have a strong base reacting with a weak acid. That's the most common idea. That's all you need to identify. Yeah, if a weak acid reacted with a strong base, then the solution is basic. That's it, and we can figure that out. Look at this. I've already written that down for you. So KCN would be KOH plus HCN. Now KOH is a strong base. This is a weak acid. There you go. This is count number one. I'm just going to tick it. Yeah, so I've got one there. First one itself. Okay, this is strong. This is strong. I get neutral. So yeah, neutral solution. That doesn't work. What is this? This is weak. This is strong. Relatively speaking, if you just Google oxalic acid is weak acid, sure, maybe. But when you compare both of these, this is much stronger. Yeah, it has a very, very low pK value, something like 1.5. This is going to be an acidic solution, not on our list. This one is strong. This one is strong. Clearly, most simple thing. Neutral solution, not it. This is strong. This, what is this? ZNOH? Yeah, this is weak. I think this is weak. So, is it going to work? Oh no, this is also acidic, right? So this is also not going to increase the count. Wow, just one so far. And we're going through this pretty quickly. FeCl3, interesting. I have FeOH whole thrice and HCl. Okay, well this is definitely strong, and this is much weaker than this. So, yeah, this is an acidic too. Just one so far. Let's see what. Oh, we have how many compounds remaining? 3 of them. Let's see what happens here. K2CO3. KOH is strong. H2CO3. Yeah, this is kind of weak. There you go. One more. So the count I have so far is 2. Yeah, I have 2. Because I need to report how many of them are basic, how many of them turn red litmus paper blue. That's what I'm counting. NH4OH, this is weak, this is strong. Yeah, there you go. This one also acidic, not happening. LiOH, yes, strong. HCN, weak. And there you go. Oh, wrong one. Yeah, this is correct. So I'm going to put a tick over here. And the answer is 3. The idea behind this was simple. I went through that because you need to be able to do this quickly. Yeah, why would a salt be acidic or basic? When you put it in water, if the ions hydrolyze, then you can figure out which way it goes, acidic or basic, and that will be based on this idea, whether the initial acid or base, assume that some acid and base reacted to give you the salt, the relevant salt, and then that hydrolyzes. If you figure out the initial acid and base, then you can get to whether the salt is going to be acidic or basic, which we just did. Answer is 3. Okay, so what we have here is the Fischer projection of D-glucose, and need to convert that to beta-L glucopyranose, and this is a ring form. Okay, what are we going to do? What's the approach going to be like? Well, look, this is not really a trick so much so as how to approach problems like this. Yeah, this could give you easy marks from biomolecules. You have alpha D glucose, you're moving this to beta L pyranose, the ring structure. Now, what is alpha, what is beta, what is L and D? That's all you need to know. So alpha is when you have OH on the right on the anomeric carbon, okay, and L is basically the mirror of the D, the ring structure, which is the Pyranose structure. That's all you need to know. So we're going to quickly draw this, and if you ever have a doubt in this and you're unable to remember it, just come back and look at this video. You'll be fine. You'll solve literally any question on these ideas. So let's get started right away. So what you have on your left is the D-glucose structure, and that's in the question, nothing new here. And if I want to get to alpha D glucopyranose, what do? Well, this bond form, yeah, this is an anomeric carbon, and this gets formed. That's what I say on the right over here. So I'll name that as 1, 2, 3, 4, 5, and this is carbon number 6. So this is alpha D glucopyranose. This is because OH is on the right hand side. Yeah, it stays over here on the anomeric carbon. But I don't need alpha, do I? I need beta. Yeah, first I'm going to convert this beta, and then we'll figure out the L idea. So let me quickly erase this and replace that here. So OH is on the left hand side, H is here. And that's it. So this now becomes beta D-glucopyranose. Now, what I need to have a flash, I need the ring, the pyranose structure. How do I get that? Everything on the left is basically going to be on top, right? And on the right, stuff goes at the bottom. Yeah. So this is everything on the right goes to the bottom on the ring. So this is what the ring will look like. Remember this number, and there's this O over here. This is that same O. This is carbon number 1, carbon number 2, carbon number 3, 4, 5, and this is 6 on top. Yeah. So when you make beta D glucopyranose, this is what the structure looks like. Okay. Look at this again if you don't remember this. Yeah. See them side by side. You have the Fischer projection and also the ring structure over here. And as again, this is extremely important. Everything on the left goes on top, everything on the right goes to the bottom. And we switched sides when we went from alpha to beta. Alpha was OH on the right, then we put OH on the left, okay, when we made it to beta. Last step, we need to get beta L glucopyranose. What's that? This orange line here is showing that I'm just flipping this, yeah? So this is like vertically flipping it, which is just the pink things, all of them. I'm just flipping wherever there's OH and H, just flipping their positions. And what you have over here, oh, there's another H over here, right? Yeah, there's an H over here. Okay, so this structure is basically going to be beta L glucopyranose. That's it, that's your answer. So we took some time and did this, a little bit of theory, but hey, if you're okay with this, trust me, you can solve literally any question on these ideas, and this should give you immense confidence. Answer is on your screen right now. This question can have more than one correct answer. And what's happening here is there's some cis and trans isomers, some reagents, and some products are formed. Now these products are, the options say that, okay, they can be enantiomers, diastereomers, and addition. There's something in the option that tells you what's happening here. It's talking about addition. So maybe there's an addition reaction that's happening here. So what's the approach going to be? What we're going to do is, well, obviously you start with cis and trans isomers. If this bromine, when added, it gives you, they're both added on the same side, it's called syn. A little bit of theory. If it's added on the opposite side, they're called trans addition. This is clearly an addition reaction. Bromine is being added in the presence of CHCl3. So that's what's happening here. The double bond breaks. What our approach is going to be slightly different than the other numericals we did. We're not going to eliminate options here. We're going to figure out the theory, and I'm going to tell you a really, really neat trick on how to solve all kind of addition reactions when you have syn or anti-addition. Again, on the same side is syn, opposite side is either trans or anti. It's the same idea. So what's happening? Is it anti or anti or syn? Well, Br2 happens to be an anti-addition. Br2 in the CHCHC, this is an anti-addition idea. And if syn addition examples are K1O4 and osmium tetroxide. That's really, really important. Yeah, theory-wise, remember this. You can solve literally any question on the idea of addition to a double bond, whether it's when you're doing isomerism specifically. So pay attention to this question. Okay, and lastly, we need to figure out what kind of product it is. Now, these names, trio and erythro, this is what they're called. They are not as important as what the structures they represent. What is the structure? Okay, trio is addition on the opposite sides. This is what it looks like. If A is being added to a double bond, and this was what it would look like. If it's an erythro product, it would be on the same side. Easy way to remember this is that E has these lines all on the same side. So, which means that erythro products are formed. Okay, I'm gonna go do a little bit more theory and then give you the trick right away as to what you can do over here. So on your screen over here is a elaborate reaction. If you have a cis isomer, the first one, R1 and R2 groups, and this is a double bond right over here, and we've taken H over here. These could also be different R's, but let's do it this way. This is keeping things simple. Now, we're only looking at anti-addition, and what I'm adding is, say, anything A, because bromine is anti-addition. Then you get trio product, which is this way, yeah? These are on the opposite sides. And the mirror image. That's why you get two products even in the question. That's why that's given, because they're considering this and the mirror image. So these two products are formed right here. Now, what happens on if you have a trans isomer? Now, if you have a trans isomer and anti-addition happens, you get erythro products. Okay, these are the two erythro products that you get over here. These are the mirror image. Remember, erythro is same side and this is the same side. If R1 is equal to R2, which is happening in our case, yeah, both of them are CS3 groups, then you just get one product, and that's the meso product. How's that? Well, you will have a plane of symmetry, which is given by these lines over here. Yeah, so that means that these are both the same compound, and that is the meso compound. So if it's the same compound, why have they given it different alphabets? Just to confuse you. So be careful about that. Now on to the actual trick. Yeah. Now if I start with a cis isomer and the product, then the reagent that is added, it causes an anti-addition, then I get a trio product. Okay. This is, you can remember, this is C, A, and T. Now, if either one of C or A change, which is if I make cis to trans or anti to syn, then I get an erythro product. Okay. If both change, then nothing happens. Yeah, it remains as trio. Let me write that down quickly. Before that, remember, E is on the same side, okay, which is over here because of these things on these things being on the same side. So all the four possibilities. Yeah, if I have cis and anti, I get trio. If I have trans and anti, so I've just changed one thing over here, this becomes erythro. Now if I change the other one also, which is trans and syn, then I get trio again. And the last one, what would that be? I would have cis and I would change the second one to syn, and I would get what? Well, I would get erythro again. So this is the easiest trick to do this. I know we did more theory in the beginning, but that was something you would do before in a class or something like that. But the final result of this trick is basically this thing right here, figuring this out and getting these different forms based on what's changing. Now, looking at that, let's apply that here. We had trans and anti, that will give me E from that same idea. Remember, it was C-A-T. I changed this to T, this remains as E, so this becomes E, okay? That's what I use to get this. And cis and anti gives T, which is the same as the C-A-T idea. And I've drawn these structures over here. So this is what M, N, O, and P are actually going to be like. Now, M and N are identical, right? Remember, plane of symmetry, this is a meso compound. These ideas can also be tested at times, okay? In this question, we don't talk about it, but it's extremely important theory-wise. So they're identical, and these are M and N, these are O and P. Now these are enantiomers. Okay, I know this approach is kind of different. I'm teaching you the theory in this question. We'll figure out the options. Don't worry, we'll definitely get this question correct. There's no chance of going wrong. Yeah, this theory is extremely important. All right, these are enantiomers, and the other combinations, yeah, which is basically M and P and O and N, they're going to be diastereomers. So let me write that down. So O and they're the same compound M and N, but anyway, ON or OM and PM or PN, these are diastereomers, which are non-superimposable, non-mirror images. Okay. All right. There you go. Okay, now let's look at the options. We've done the theory in detail. Let's look at the options and see which ones are correct and which ones are not. So, what you have here is, first option is MNO and NNP are two pairs of enantiomers. No, definitely not. Yeah, we have already figured out which ones the enantiomers are. They're just one pair. Yeah, the other ones, the same compound. M and N are identical. All right. Bromination proceeds through trans addition in both reactions. Sure. Trans is the same as anti. We already said that. This is theory you need to know. Okay, that bromine in presence of CH_Cl3 is anti-addition. Osmium tetroxide as well as KMNO4 give you syn addition. Okay. O and P are identical molecules? No. M and N are identical molecules. MNO and NNP are two pairs of diastereomers? Sure. We already marked that out when we were figuring out this. So there you go. These are the correct answers. We spent some time on this because this theory will help you solve literally any question on the idea of addition when you're doing stereoisomerism.
For more videos and live lectures on the JEE, click on the subscribe button now.